Welcome to Chapter 15, Determining KSP using Molar Solubility. So, the question states to calculate the KSP for silver sulfide if 0.48 grams is dissolved to make 250 milliliters of solution. First, let's just go ahead and establish what KSP means. KSP is the solubility product constant. And it involves salts that have limited solubility in water. You're using it for, use for salts with limited, sorry about the messy handwriting, solubility in water. So in this case, we have silver sulfide. And what you'd want to have memorized, hopefully by now, that silver is not super soluble. There are some things it is soluble with, but sulfur is not one of those things. So step one is to identify our major species. And there's really only one option. That makes life easy. Ag2S, and we know it is a salt because we have a metal with a nonmetal. Again, either one of those could be replaced with a polyatomic and it would still be a salt. All right, now, as usual, we're going to write out the reaction. So when you are dealing with a salt, it is good to start off with splitting it up into its pieces. Now we have to figure out, are we going to use a double arrow or a single-sided arrow? In the last two videos, since they were salts, we just used a single-sided arrow. However, we know this is not soluble, or at least very, very insoluble. It's maybe kind of a tiny amount soluble. And if that's the case, that means we're going to have some left over at the end. You can use a double-sided arrow here. So we've got silver and sulfide. And if you wanted to add a little note, you could say use this because not completely soluble. All right, now step 3. We will either do a dilution or write the equilibrium expression. In this case, we are mixing a solid in a certain volume of water, so it's not necessarily a dilution, but there will be a molarity involved. I'm going to go ahead and write my equilibrium expression first. So write equilibrium expression. KSP is equal to, so now we know we started with a solid. We are dissolving it, so it must have been a solid at the start. Here, I'll add those labels. And then it's dissolved, so we end up with aqueous and aqueous. So keep that in mind when you're writing this expression. We're going to put our silver. Now be careful, we have an exponent. We use those coefficients as exponents. Now, are we going to include the original solid in the denominator? No, we are not. We do not include solids or liquids. And we're going to try to find KSP. In order to do that, we need to know the concentrations of each of our ions. So let's use what they've given us here. Solve for molarity. You could also write this as solve for concentrations, same thing. We know that we have 0.48 grams of silver sulfide. And if you went to your periodic table, you would find that there are, let's see here, I want to change this into moles. So I've got 1 mole per 247.66 grams. Okay, so my grams can cancel out, they're in a diagonal. So this tells me, actually, yeah, let's find out what that number is. So I have 0.48 divided by 247.66. Okay, so I'll end up with 0.001938 moles of my Ag2S. Okay, but I want molarity. I know the volume that it's placed in, 250 milliliters, which is the same as 0.25 liters. So I'll say 0.0019. Well, I only have, well, I'll just write this out, that's fine. 38 moles over 0.25 liters. And let's see what that comes out to. I only have 2 sig figs, so 7, 8. 7, 8 molarity Ag2S, and I can use that to figure out my molarities of the different ions. So let's see, you can use mole ratios to figure this out, but we know there's a 1-to-1 between sulfur and Ag2S, so my sulfide is the same. And I'll write this out to help you. Oops, I got these charges backwards. This should be 2 minus, and that should just be plus. Okay, so for my silver, it's 0.0078 Ag2S, and I know that there are 1 of these for every 2 of these. So I end up with 0.0078 times 2, which gives me 0.0156. That's too many sig figs. 0.016 molarity of my silver. So I'm just going to move on over a little bit. Step 5 will be to plug in our numbers. Plug into equilibrium expression, because that's the whole goal of this whole problem. So our KSP is equal to 0.016 squared. Do not forget that. Be careful. Don't be the person who forgets it, because I'm sure someone will. 0.016 squared times 0.0078. And you're going to end up with 1.9968 times 10 to the negative 6. However, that's too many sig figs, so I only want 2 sig figs. 2.0 times 10 to the negative 6. And that would be our KSP, our solubility product constant for silver sulfide.